The next analysis mode in PredictK is dynamic conductivity analysis. In this mode, PredictK accounts for a number of flowing and damage factors that occur in a proppant pack. The first conductivity detriment actually comes from the fracturing fluid used to create the fracture and deliver the proppant. Based on reservoir and fracturing fluid properties, PredictK calculates a percent retained permeability and a filter cake thickness that is expected to occur. PredictK also adjusts for permeability reduction resulting from the reservoir fluid. These adjustments include non-Darcy effects from the velocity calculated through the proppant pack and relative permeability effects based on the fractional flow of oil, water, and gas. These relationships are based on 30 years of proppant testing data, and both the governing equations and testing information are available to Proppant Consortium members at the Proppant Consortium website. For this video, I will continue working in dynamic conductivity mode with the PredictK demonstration file available alongside this video group. I'm actually going to start from the point we ended at the end of the baseline run from the previous video. So using this file, under the Treatment tab, double-click on one of the treatments to open the Treatment Edit screen. You will see a number of options that were not available in baseline conductivity. First, fracture height, bottom pressure, and surface gas rate can be entered. PredictK will use these values, along with calculated internal width, to find a velocity for non-Darcy flow corrections to permeability. In dynamic mode, you can also input a filter cake thickness and percent retained permeability. In general, the default values will be sufficient to provide useful results. Obtaining a better estimate of both values requires fluid cleanup testing with the field fracturing fluid and the reservoir core. Moving on to the Well Information tab, the inputs look fairly similar to baseline conductivity. In fact, all of the repeated inputs still have the same effects on proppant pack conductivity. This includes the bottom hole temperature, the number of cycles, and the Young's modulus. Added inputs are related to the produced fluid other than the main produced phase. Water rate can either be set manually using constant rate or set as a factor of oil or gas rate, depending on what your main fluid type is. The remaining hydrocarbon phase is set as a ratio to the main produced fluid. Since this is a gas well simulation, both oil and water are input as barrels per million standard cubic feet of gas in the default units. If we expand all the tabs, you can see the units required shown on the screen. Finally, running the simulation will populate many of the same graphs that are available in baseline conductivity. The only difference is the final value, which is now much lower because of the additional factors being accounted for. When you compare the baseline and dynamic conductivities in this project, you'll notice that the baseline values peak at around 3,300 millidarcy feet, and the dynamic values are much lower, peaking at 190 millidarcy feet. This difference is in line with what has been reported in numerous SPE papers over the years. In fact, the values quoted in a number of those papers actually came from PredictK simulations. With this information, you should now be able to use dynamic analysis to find realistic conductivities under reservoir conditions. This can help you develop reasonable expectations for relative well performance of different fracturing schemes from whatever reservoir model you might be using. In the next video, we'll be using PredictK's production analysis mode to find those estimates for well performance. Thank you for taking the time to watch this training video, and if you have any questions, please contact me at steven.driley@corelab.com.